All right, this is the more detailed video for the hardware version of Lab 4. You're going to be getting at least one infrared distance sensor, which works pretty similar to our brake beam encoders, but instead of sending the IR light directly to the receiver, it's instead waiting for it to bounce off some surface and then come back to the receiver. And then it uses the time that took divided by the speed of light divided by 2 because you're going there and back to find your distance. You're going to be getting at least one of these as well as the data sheet on Canvas to help you wire it up. They should all have leads already, so that should be pretty much good to go. When you get your IR sensor, you're going to have to characterize it. You're going to use the analog read serial, just like we did the digital before. So that's under File, Examples, Basics, Analog Read. You're going to be giving it an analog pin, which is A0 through 5 on your Uno board. And then as you run that, you're going to set it up with a tape measure and some reflective surface. I find that a white binder does pretty well. Something that's not flimsy is going to be the easiest for you. And then as you're doing that, you're going to take distance readings along your tape measure and find out what the associated analog output would be. And then you are going to plot it in the chart that was given on Canvas. Here's where you'll put your analog reads, and here's where you'll put your distance measure on the tape measure. I'm not sure why these have so many digits. You don't have to use that many. I would say probably eighth or a quarter of a centimeter is fine. And then this has a bunch of extra columns just to show you the different types of estimations we could do. For example, if we were to plot directly distance versus voltage, we'd get this kind of odd looking curve. That's because the usable range of this sensor is about 3 or 4 centimeters to about 30 is where it's most accurate. Anything less than 3 and it kind of freaks out. So that's not in our usable range. And then another way we could do it is if we plotted our distance plus a constant and the inverse of that, we get this nice line here that can be good for estimation. And then here's our linear fit. Here, if we take the inverse of the distance directly, we kind of get a quadratic leaning toward it. So a linear fit doesn't do as well as it does if you had our distance plus a constant and then the inverse of that. And that is all generated here in these datas. And it just shows you that the direct inverse has a much higher error than the inverse with the constant added in. So you don't have to really change any of that. That's just showing you how our estimated works. Here is where you will build your linear fit. You'll probably want to use this equation instead. So mess with the M and the B to try and minimize this number as best you can. And then we'll use that linear fit in the Arduino code. So as soon as you've got that set up, you're going to code it into our Lab 4 code. Just a quick walkthrough here. Here's our interrupts, just like Lab 3. If we don't have enough IR sensors for 2 for everybody, some people will be getting the ultrasonic distance sensors, which pretty much does the same exact thing except with sound instead of infrared light. And then you'll need this library for those, which I will include on Canvas. You'll extract it into documents, Arduino libraries, just like last time. There's mine. Then we have all our constants from Lab 3. We'll need those again, all the definitions as well. And then here's some new things. If you have 2 IR sensors, you're going to give them each a pin number in the analog inputs, or you might just have one. If you're using an ultrasonic, they have a trigger pin and an echo pin. And that's set up here either as your side or your front. Just comment or uncomment, whichever one of those you need. Then we have a wall tolerance. What distance do you define as a wall existing? Is that 3 centimeters? Is it 5 centimeters? I wouldn't recommend any less than 3 because, like I said, that's outside of our usable range for the IR sensors at least. Then we have an empty moves list because we're dealing with an unknown maze, and I made it nice and big for you. We probably don't need 50 moves, but just in case, we're not too worried about space on our microcontrollers since we're doing pretty simple programs. So 50 integers is fine. Then our normal setups here. Same thing. This is the same exact content as Lab 3. We haven't changed anything here. But for the loop, we're going to do quite a bit more functions than we used to because this lab takes some extra steps. So we're going to wait for our push button like normal. And then the first thing we're going to do is we're going to set our robot down in the spots place. And after we press this button, it's going to explore. So it's going to follow either the left hand or the right hand rule. And that comes from a basic algorithm for maze solving. Basically, if you're in a corn maze, and you keep a hand on the wall, as long as it's set up in a certain way, you're always going to get there. So for instance, let's pick a good lab. There we go. So for instance, if I'm going to follow the left hand rule, pretend that I'm standing where this arrow is, and I've got my left hand on the wall. I'm just going to keep going to keep my left hand on the wall. So which means as soon as the left wall goes away, I'm going to go ahead and take that turn. But as soon as my front and left are blocked, I turn right instead. So I'm just going to keep following that algorithm. And eventually you reach the endpoint. And that will be true for any of the mazes that I'm going to give you in class here. So we use that logic to explore the maze. You can choose either the left or right hand rule. It just depends which side of your robot you attach the sensor to. And then here's that code. This is, you'll have to fill it in for yourself. So we're going to read our side. If there's not a wall there, if the side distance, actually that should be a greater than. Greater than our tolerance means there's no wall. We want to go ahead and take that turn and drive forward into it. And then we want to record our actions into the moves list. If the side is blocked, but the front is free, we're going to go ahead and drive forward. Otherwise, we're going to turn away from the side and then continuing to record our actions. And we will do this in a loop until we hit our front button, our start button. We're also going to use that as our finish button to tell the robot that the exploration phase is finished. Here are some helper functions for reading those distances, whether you've got IR or ultrasonic. After it's done exploring, it's going to stop and let's go ahead and do our solve. So solve will be something that you write all from scratch, and you're going to take your moves list and edit it or copy it somehow so that all of your dead ends are gone. So for instance, in this one, what I wanted to do, instead of turning left here and doing this whole long thing, I would find that pattern, which is indicated in this case by a double right, just like I showed in the overall video. So somewhere in your Arduino code, you want to go through this. There we go. Here's another dead end. See what that did so far. Oops. That's totally wrong. Let's start over. So this is one of the edge cases. We're actually facing a dead end. So that's one of the things you'll have to look for. There we go. So you can go ahead and test this function by giving it this list that you generate with this GUI code, seeing if it comes out correctly to what you would solve it manually. So I really recommend using this GUI tool to help you identify patterns and to make sure that your solve algorithm works correctly. Um, After your algorithm is solved, basically you can just go ahead and do our lab 3 code and run your new maze list. I like to include this run in an infinite while loop. That way you don't have to re-explore every time you want to run, just in case there's a little mistake, you've got it lined up incorrectly, something like that. So I have it with a button push in a little infinite loop. And then if you do want to explore again, that's when you'd hit the reset button, or you could unplug, replug your battery. And then after, here it is, the run maze. That's just pretty much, you can go ahead and copy your lab 3 loop that we had for running through a known maze, because now the maze is known, you've solved for it. You're also going to need your drive, your turn, if you have reactive control, and then the PWM commands from lab 3. And then here is your standard encoder encounters. And that should be general overview of the hardware version of the lab.